Hi guys, in this video we are going to still talking about binomial probability distribution. That is one more thing that we're going to discuss about it. Alright, actually not one more thing, there is still several other things, but for this video we are going to focus on talking about binomial probability distribution table. So in reading cumulative binomial distribution table, right, we know that there are three things that we need to look at. First, the value of n, and then the value of p, later the value of k or x. Okay, however, if you look at it carefully, you are going to see that our table there, right, for p, we only have p up until 0.5. So it literally means that you will have a problem to find the probability of situation that consists of p that is more than 0.5. Okay, so there is other table out there that being developed that have p more than 0.5. You can try to look at it after this, but in the case that you have this kind of table where p is just until 0.5, right, that's a way to deal with it. Okay, so let's try to do that by discussing example 2.10. Okay, so for this case, right, according to table provided by National Center for Health Statistics in Vital Statistics of Malaysia, there is about 80% chance that a person aged 20 will be alive at age 65. Okay, that is the information. So now, given that information, suppose 10 people at age 20 are selected at random. Let us attempt to use cumulative binomial distribution table to find the probability that at least 8 will be alive at age 65. Now, let's try to extract out. First, let's try to make it a habit, right? Let's try to see whether this is binomial or not. So they are saying that 80% chance that person age 20 will be alive until 65. We'll see one percentage there. So what about the other 20%? Meaning the other 20% will not be alive at age 65. So two outcomes. So binomial. Now they want us to find the probability at least 8 people will be alive at age 65. So basically px more than equal to 8. Oh, before that, let's talk about the random variable. What is the random variable for this question? What is the interest? So let's look at the question. They want us to find the probability that at least 8 people will be alive. So they are interested to see the probability of people that are alive. So what is the percentage? 80%. So our random variable is the number of people, the number of person age 20 that will be alive at age 65. Okay, so what is the p for that variable, for that random variable? 0.8 or 80%, right? So let us write that down first. We have x approaching to b. So we have n 10 people, right? 10 with p 0.8. Okay, so what is the probability that x more than equal to 8? One way is to just use a manual calculation, right? You have the formula, right? You just calculate the formula of 8, x8, x9 and x10. Only 3 calculation and you can get the probability. However, this question specifically tell us to use cumulative binomial distribution table to find the probability. So whether we want it or not, we need to use the table. Okay, so since 0.8, right, is not in the cumulative distribution table, we should manipulate the definition of success. What does it mean by that? Up until now, our definition of success or the interest is on those who are alive, 0.8. So we'll need to change it instead of looking at those who are alive, we look at those who are not alive, which will change the P, or the success rate. Instead of 0.8, we look at 0.2, which will later actually available in the table, 0.2. So, however, it is not that simple. You can't just flip the coin. You will need to change everything. So, when we are looking at those who are alive, and they want us to find more, at least 8 people that are alive. So when we are looking at those who are not alive, which is later it is 0.2, the question will also need to be changed. Instead of looking at the probability of at least 8 people will be alive, we'll need to change what is the probability that now we need to figure out how many people that will be dead, will not be alive, if at least 8 people is alive. That is what you need to figure out. So let's try to do it this way, right? Let's play if, right? If then. If 10 people is alive, how many people not alive? For this case, they are selected 10 people, right? So if 10 people is alive, 0 people will not. There is no people that is not alive, right? Because all of them alive. Now, in the case of 9 people alive, what is the probability of, what is the number of those are not alive? 1 not alive. So if 8 alive, we are going to get 2 not alive. And you can go on until if 0 alive, you will get 10 is not alive. So by looking at that, right, in the case of at least 8 alive, if you refer to that one, in the case of at least 8 alive, so in other words, what if 8, 9 and 10 alive? Right? What is the probability of 8 people alive, 9 people alive, 10 people alive? In this situation, let's go to the other way around. Those who are not alive, what will be? What is the probability that 2 not alive, 1 not alive, 0 not alive? Right? Now we redefine the random variable, but first x is for those who are alive, so we change it to y, those who are not alive. Okay, and then instead of looking at more equal to 8 alive, we look for less than equal to 2 not alive. So now instead of using looking at 0.8 and more equal to 0.8, 80%, or less, and with x more than equal to 8, now we look at less than equal to 2, right, for 0.2%, 0.2 p, right? So just substitute it and you should get 0.6778. In other words, the probability that at least 8%, 8 people age 20 will be alive at age 65 is 0.6778, or approximately 68%. Okay, you might be questioning, how can we use the probability that we just calculate, which is for those who are not alive, toward for those who are alive, right? Basically, what we are doing is we are reflecting at we are looking at the same things, just at a different side. So that 0.6778 can be the answer, can be the probability for at least 8% who are alive, or at most 2% that are not alive. Okay, so that is how you actually look at solve the question by using binomial table if it is more than 0.5. Now let us discuss a bit on the effect of N and P, which is the important input for our binomial, right? What is the effect of the N, the size of N, the size of P toward the shape of binomial probability distribution, is to show you how important is that input. Okay, so if you look at this graph, you will see that the top three there, right? It shows the figures, right, when we play around with the p, the value of p. So in that case, right, we are using the same example as we have discussed before, where the n is 10, right, and the n is 10, so p is 0.2. Okay, so if the p is small, the distribution is skewed to the right, right? If the p is 0.5, it will be symmetry, and the p is 0.8, it will be skewed to the left. Okay, so now let's see what happens if we play around with the n, the value of n. So when the n with the same p, which is for this case 0.2. So first, if you just as we have discussed before, you look at the top graph. If the n is 10, the p is 0.2, you will see right skewed. However, if we increase the value of n, as you can see, the shape of the graph, right, slowly change, right, to symmetry, approximate symmetry. If we increase the number of n even further, you will see that it becomes exactly a bell-shaped distribution, or distribution that we are going to learn later. We call it a normal distribution shape. Okay, so we are going to use this kind of knowledge later in the next topic. Okay, so that is about binomial distribution. In the next video, we are going to proceed with the next distribution of discrete, which is known as Poisson distribution. So, thank you.